Hello, this is CSM Worksheet 7 walkthrough question 1, recorded during spring break for some reason, but let's get started. So, let me preface this question a little. This question is quite a long question, and it touches on the fundamentals of how capacitors work and tries to give you more extended practice about how to apply these concepts into different types of capacitor problems. Some of these question forms are more creative than what the homework and past exams have been showing, so they're a little hard to configure on your own perhaps, but in this walkthrough we'll try to go through the intuitions and hints and how you can walk through these kind of questions when you meet more creative forms of asking on exams and assignments. So let's get started with question part A, which the screen is already stopping on. Suppose we take two conducting disks of radius r and place them on a distance 2r from each other parallel to one other with air in between. Calculate their capacitance in terms of the variables r, epsilon naught, and other constants. So I'm going to go through parts and parts of me lecture about capacitor features when we go through the problem so that we still have an idea of what's going on. And now is one small mini lecture about how capacitors are supposed to work. So usually we build capacitors in a form that looks like this. We will see two plates. They're usually conductors, they're conducting plates that are parallel to each other on the capacitor. And within these two planes, there will be a substance, or there will be a thing in between these two plates. And the charges of a capacitor and the capacitor is supposed to store charges within the circuit. So this substance is going to help us store things, or store charges in the circuit. And the way that this substance in between the two parallel conducting plates helps us store charge is by raising a metric of a capacitor called capacitance. So C, which stands for capacitance of a capacitor, is equal to kappa epsilon A over D, which is also written in your lecture as epsilon A over D. So here are what these variables specifically mean. Kappa stands for a dielectric constant, and epsilon naught means the permittivity of free space. These two combine together as a product into the variable we know as epsilon. So the higher the epsilon is, the higher the capacitance is, so the more charge you can store in a capacitor. So capacitance stands for the capacity of a capacitor. And hopefully this wording makes it a little more intuitive to understand, because C is the capacity of a capacitor, which is why it's called a capacitance. You mention the capacity prefix in each of the words here, which stands for contain. A here in the equation means the overlapping area of the conducting plates. Notice that it has to be an overlapping area. And last but not least, D stands for the distance between the plates. And having two plates being parallel means that the distance between the plate is equal throughout the entire plate area. So now let's try to use this formula, C is equal to epsilon A over D, to solve the above question. So notice that the question also says that between the capacitor there's air. So if it's air that's between the capacitor, then we directly state that the permittivity of space is epsilon naught, which is a constant, and the dielectric constant of air is supposed to be equal to 1. So this is also another constant to remember. Now, C is equal to then epsilon naught times A over D. Suppose that our Suppose that our conductor plate is actually a disk of radius r, which means the area is equal to r squared pi, and they're at a distance of 2r between each other. Then the capacitance of this capacitor is equal to epsilon r pi over 2, which is simplifying the fraction we have here using the formula of a capacitance. So now that we have figured out this question, let's move on to the next one. A variable current source is hooked up to the ends of a capacitor as given by the following circuit, which I am not sure if they included a circuit for this question. They probably didn't. I'll draw it out later. The current source emits a current as a function of time given by what we call the function here, ist is equal to 200 times sine of this function, with t given in seconds. Calculate the charge on the plates of the capacitor after 6,000 seconds. So with that, we'll first have to review what is the relationship between current and charge. I know that I is equal to, or the current is equal to, the rate of change of the number of charge on a circuit element with respect to time. So I is equal to dq dt. I'm going to integrate this expression from 0 to t elapsed, which I'm just going to write as te, for both of the functions here. And it turns out the right side is equal to the amount of charge at time elapsed minus the amount of charge at the 0th second, which is equal to 0, because the capacitor started uncharged. So let's try to calculate the amount of charge here by integrating the current function over the time period from the 0 second to t elapsed. I'm going to do the expression here, so I'm going to have to integrate sine somehow. Alright. So now I'm going to try integrating this function. And I will then get that I have to integrate this as, well, first I'll have to calculate the antiderivative of this. I'm going to move the 200 to the outside of the integral so it's easier to make the integral. So we can either mechanically calculate this integral, which is the more intuitive solution to this. I'm going to do this to you. I'm going to do this for you. Is equal to, well, I have to integrate sine. It's going negative cosine. The derivative of negative cosine is sine, so I know that the function has to be something negative cosine. And maybe I have to multiply this by 1000 over pi, so that when I take the derivative, I can cancel out the coefficient that is resulted from the chain rule. And note that I have to do this from te to 0, which is equivalent to 200 times, negative 2, I'm going to say that this is equal to 200 times negative, I'm also going to put 1000 over pi at the beginning, so that I can not care about that later, and times negative cosine, t is 6,000 seconds, so I'm going to substitute 6,000 here, so that's cosine of 6 pi, minus negative cosine of 0. Turns out that these two values are equal, so the final answer of this integral is actually 0, which means that the total amount of charge after time elapsed is actually 0. So let me show you another way of doing this. Say that I have the t-axis here and the vertical axis is for the value ist. If I look at the function of the current here, see that this is equal to 200 sine pi t over 1000, and you might remember from your high school algebra how to plot this thing, but I'll just plot it out for you now. And then we can observe something very interesting from the graph. So the graph should look something like this. I'm going to mark the amplitude here. And we're going to draw a sine wave across here, which might not be totally accurate, but note that the amount of charge we get is equal to the area under the current curve. And let's try to look at what is the area under the curve for the current function. You see that this part of the curve and this part of the curve has a total of 0 at the area under curve because they cancel out. And I can see the same thing happening for the area of curve between 2,400. Finally, I can see the same thing happening for the curve area from 4,000 to 600. So the total area under curve is 0. And once again, this is because this is a sine graph. So either way, we get that the total amount of charge after 6,000 seconds would be 0. Now let's move on to the next part of the question, which is part C. So now we're going to talk about another interesting property of capacitor, or actually two. One of them is called energy, and the other is called conservation of charge. I'll go through them as we go through the different subparts of the question. For now, suppose we have a circuit given by what you have seen on the monitor, and note that the arrow of the switches at time t1 will activate at the direction of the arrow when it comes to the time related to the switch. So at time t1 and at time t2, we'll have entirely different circuits going on. First, let's try to calculate the total energy in the capacitors before t1. Assume that the capacitor C2 starts off as uncharged. So to do that, we have to first draw out the circuit before t1. So let's look at what happens. What does the circuit look like when it's before t1? I'm going to draw the basic parts of the circuit, with the switch parts being empty so that I know what to do later. Okay, so well, first of all, T2 is only closed, the switch of T2 is only closed when it's time for T2, so this part is definitely an open circuit. The switch hasn't been connected yet. But for the part of the T1 switch, before T1 it is actually closed, and it is after T1 that is open, so I have to connect this part. So with that being said, this part of the circuit will not have any current flowing through it, because there's no pathway for the current to flow through it. The current flows from Vs to C1 and then flows to the ground. There's an open circuit here, so the current cannot flow in the direction of C2. So with that being said, now I just have to know how to calculate the energy across the capacitor C1. Note that the formula of energy is equal to 1/2 CV squared, where V is equal to the voltage across the capacitor. So for us, this the total energy in this circuit is only collected by capacitor C1. So the energy is equal to 1/2 C1 Vs squared, as Vs is the voltage across C1. You can see that this node has a voltage Vs and this node has a voltage of 0V. So once again, at the end, we get that the total energy is equal to 1/2 C1 Vs squared. Now let's look at part D. So after time t2, calculate the new total energy in the capacitors. So let's draw out the circuit after time t2. After time t2, first of all, at time t1, the first switch opens, and at time t2, the second switch here, corresponding to the switch of t2, closes. So we get a very similar circuit from what we have above, except now t1 is open and t2 is closed. So I'll draw the circuit out. Once again, t2 is now closed. And passive sign convention. So here is a property of capacitor that you will mention, you will learn more about in the next week, which is called charge sharing. Well, when I say next week, you probably have already learned it since I'm recording during the spring break, which is kind of late. But you will learn a property called charge sharing, which means for any charge that is on the capacitor or on the plate of a capacitor, and if the charge cannot escape anywhere, it's going to be kept in the circuit. So for example, the charge on C1 during before T1 is going to be kept on the plate of C1 because there's no way it can escape to anywhere. There's no way for the charge to escape anywhere. But also I have Q1 before T1, QC1 before T1 here, and that's the amount of charge that I can store on C1 before I turn the switch of T1 and T2. But after I turn the switch of T1 and T2, there's still nowhere else for the charge to escape to. For example, before T2, right after T1, the circuit looks like this, and the charge of C1 is going to be kept on the plate of C1. But when I connect T2, now the charge on C1 is going to have somewhere to flow through, which is on the plate of C2. So QC1 before T1 is now going to be equal to the sum of new charge on QC1 and QC2. So now our charge across the capacitors becomes slightly different. And note that the amount of charge on C1 before T1 is equal to C1 Vs. This is because the capacitance of capacitor is C1 and the voltage across it was Vs. And Q is equal to CV, which is another part of capacitor characteristic. So now I'm going to try to calculate this. And first of all, to calculate the energy, I have to know the charge across QC2, and that is going to help me a bit. And furthermore, what we can see is that the amount of charge across the new circuit, which is QC1 prime plus QC2 prime, is equal to, well, if I call this charge amount of voltage here Vx, is equal to C1 Vx plus C2 Vx. So actually, in the end, I get that Vx is equal to exactly C1 Vs over C1 plus C2. So now I have the voltage across capacitor C2, and I know that the energy of a capacitor is equal to 1/2 CVC squared. Well, now I have the voltage across both of the capacitor, and I have their capacitance. I can just calculate the energy directly. So the total energy is going to be equal to all of the energy stored on any circuit. Sorry, any capacitor on the circuit. So this is going to be equal to 1/2 C1 VC, which is Vx here squared, plus 1/2 C2 Vx squared, and that is going to be equal to 1/2 times C1 plus C2 times Vx squared, so C1 plus C2 squared divided on the denominator and C1 squared Vs squared on the numerator. And I'm going to combine these two fractions together so that I finally get 1/2 times C1 squared Vs squared over C1 plus C2. So that is the total energy across the circuit, which once again is the sum of energy you get across the different capacitors that exist here. Alright, now for part E, we have another task. Suppose C1 is equal to C2 is equal to C, then calculate the difference in energy between T1 and T2. So let's calculate the difference of energy between before T1 and after T2. Let me write a capital E so it's a little bit easier to understand here. So previously, the energy we have before T1 is equal to 1/2 C1 Vs squared. So that is directly 1/2 C Vs squared. Now I'm going to subtract it by the amount of energy I have after T2. So I'm going to replace all values of C1 and C2 with C as mentioned on the prompt. And I am going to calculate and simplify this algebraic expression a little more. Get something extremely similar to what I have here. And at last I will get that the difference between the energy is 1/4 CVS squared. So now let's talk about the optional part of the question. Nowhere in this question do we ever talk about resistance or the non-idealness of any element, and we can safely assume that this circuit is a closed system. Yet, conservation of energy doesn't seem to hold because, as you can see, by switching or by tapping on the switches, we have successfully made the circuit lose a little bit of energy. So how can that happen? How can energy not be conserved? Well, for energy to be conserved, first of all, there must not be anywhere that the energy can be converted or lost in between the tapping the switch process. But here's a slightly out of scope thing from within 16A, which is that when we're tapping the switch between these circuits, it is not immediately that we have the charges instantly shared across the capacitor, and for charges to flow from one part to the other, we need a current to flow between these two capacitors. So having this current flow through the capacitor can actually cause loss of energy, either converted into heat or stored in some other electro or magnetic field that the capacitor creates. So as mentioned before, this is out of scope for 16A. So the takeaway of this question is to know that conservation of energy doesn't exactly hold when we have a switch tapping process in capacitors. And as you have mathematically proven, conservation of energy does not apply to this kind of system because tapping switches in the capacitor circuit can actually cause loss of energy. Alright, now that we have went through around 2/3 of the question, we can move on to the last part of the question. Now here we're going to talk about capacitance again, and first of all, we call the parameter epsilon, which you have seen in the lecture, as the dielectric constant of the capacitor, and gives the maximum energy a certain medium or the substance between the conductor plates can store in the form of an electric field. So this is the physics of a capacitor. But if the voltage in a region gets too big, a phenomenon called dielectric breakdown occurs, and what happens is that maybe, as you have seen in the lecture or not, your professor may or may not have exploded a capacitor during lecture. Well, my professor did. I don't know if this semester professor does. But if the dielectric breakdown happens and your capacitor explodes, then the capacitor is broken and it breaks down into a conductor because it can no longer just charge and store charges as a capacitor can. So for the following parts of the question, we will be exploring this phenomenon. First of all, note that we can use this formula to calculate the voltage across the capacitor, and this formula is called V equals ED, where E is the electric field strength between the plates. Once again, this is slightly out of scope for 16A, but it is among one of the hints that we'll see for the question. D here stands for the distance between the plates. Alright, so let's get started with part F. Suppose that now we have a parallel plate capacitor, and we're designing square plates for the capacitor conductor plates. The side length of these square plates is 5 centimeters, and the separation between the two plates is 2 centimeters. if the space between the plates is filled by air, which means we're just going to be using epsilon naught as our epsilon, calculate the maximum voltage the capacitor can be connected to before reaching dielectric breakdown, which means that the charge that this capacitor can support is at the maximum. So let's review the question demand first. We will need to first try to figure out the capacitance of the circuit. And once we have figured out the capacitance, what we can then do is to figure out how much charge can the capacitor actually support. So these two steps might intersect with each other in terms of the time we solve it. But let's move forward and see what we can do with these things. So first of all, I am going to try to figure out a formula for the capacitance of the capacitor. So in this case, my capacitance is equal to, once again, epsilon A over D. And my epsilon naught, since I'm putting air between the conductor plates, the epsilon naught is supposed to be the constant I have here. The area is equal to 25 centimeters squared. And the distance between them is 2 centimeters. I would like to convert this into meters squared later, so it's a bit better to calculate with. And also because the epsilon naught unit uses a meter instead of centimeter. So once again, this is equal to 0.0025 meters squared over 0.02 meters. Okay, so now I have the capacitance. To get the maximum amount of charge I can store, I need to first get the maximum amount of voltage that there can be across the circuit, and that is because Q is equal to CV. So let me first calculate Vmax. The maximum voltage I can store, once again the voltage across the two plates of the capacitor can be written as V equals ED, and E is the electric field strength between the plates to sustain the voltage. So this is directly equal to Vmax is equal to Emax times, and the distance between the plate doesn't change, so this times D. So now we have to figure out what Emax is. But we know that the dielectric strength of air can be just at most 3 megavolts per meter. So this is equal to 3 times 10 to the 6 volts over meter times 2 centimeter. So this is equal to 0.02 meters. So this is approximately equal to 6 times 10 to the 4th volts. So this means that the maximum charge is equal to the capacitance, or the capacity of this capacitor, times Vmax, which is the maximum voltage it can hold, and that is equal to 6 times 10 to the 4th volt times whatever expression C has, and you can substitute this into the calculator to get what the solution file has. But from here on, it's plugging and chugging inside the computer, so it is not too much significance that we should go through. Alright, so let me just review what we're doing in this question. So first of all, we're trying to see how the capacitor can reach a dielectric breakdown. That means the capacitor explodes because the voltage across the capacitor is too big, and that also translates to the amount of charge that the capacitor is currently storing is too much. So, to calculate what's the limit, or what's the maximum amount of charge a capacitor can store within itself, we try to figure out Q max, which is the maximum amount of charge that capacitor can store. And in that way we know when and how and exactly how much charge we need to explode a capacitor in a lecture hall. So Q max in this case is equal to C times V max. Q. Remember that Q is directly proportional to V because of the formula Q equals Cv. We know that V max, which is what we need to calculate Q max, is equal to the maximum possible electric field strength times the distance between the plate. And we know that the maximum electric field strength is equal to 3 megavolts per meter based on the question description. So then we get the value of Vmax, and we multiply that by the capacitance of the capacitor to see what's the maximum amount of charge a capacitor can hold. So, if the voltage across the capacitor plates surpasses Vmax, then you can explode a capacitor in the lecture hall, hopefully without triggering the fire alarm or student PTSD. So now let's move on to the next part so we can avoid having more capacitor PTSD. Now all other factors constant, which means that all of the other factors do not change from the previous question. Suppose that what we feel between the capacitor plates is replaced by Teflon, so we no longer use air. Then calculate the new maximum voltage that our capacitor can be connected to before reaching dielectric breakdown and interpret our result. So let's put the interpret part at the last and let's try to figure out what's the new maximum voltage. Once again, keep in mind that Vmax is equal to Emax times D. And Emax times D is, well, we'll have to go back and reference. Emax is equal, for Teflon, is equal to 19.7 megavolts, which is a lot. Well, volts over meter times, well, the distance between the plates is still the same. It's 0.02 meters. So once again, I plug this into the calculator to get Vmax. And that turns out to be 394 kilovolts. So here, we can then try to interpret our result, now that we have got a new maximum voltage. So first of all, our maximum voltage is higher than what we have when we had air as our substance between the plate. So I know that the permittivity or the dielectric constant of the capacitor is stronger because I have a higher Vmax, because I have a higher... Sorry, let me rephrase that sentence. So at least I know that the new maximum voltage my capacitor can have is larger than the maximum voltage I have when my air is there. And also, if we look at the graph above, we can see that Teflon has a kappa of 2.1, while air has a kappa of 1, as we stated in part A. And what that means is that the permittivity or the dielectric constant of my capacitor when I have a Teflon is stronger than when I have an air. So in both ways, I have a stronger capacitance. Let me write that down as a relationship as well. C Teflon is equal to 2.1, which is equal to kappa Teflon, times C air, which is equal to 2.1 times the capacitance from the previous part. So I have a larger V and I have a larger C, and that means I can store way more charge than I previously can in a capacitor of for an air. So what this teaches us is that what you put inside the capacitor will directly change how much charge you can store within the capacitor. And specifically, we see that if we have a Teflon, the capacitor can store more charge. Alright, so now we have gone through the walkthrough of question 1. And if you have any question, feel free to leave them in the comments or ask your junior mentor. I'm gonna go enjoy my spring break.